All right, we cannot lose sight of the fact that we have a goal. Right now, that goal seems like it is a mile away, and yet I am moving in that direction. The goal is to be able to look at an element and see how many electrons it has and where it's located on the periodic table and go, ah, I know what that element's going to do. That element's going to give 2 electrons. Or that element's going to take 2 electrons because of this and that and this and that. In other words, by the end of all this craziness, I will expect you to be able to look at the periodic table and, due to the way the electrons are arranged around the nucleus, be able to tell me how an atom's going to act. But I have to admit, it's been a crazy ride. Okay? If you take out your worksheet, you'll know that what we've tried to figure out, first of all, is what are these things? What are electrons? And the first thing we realize is that electrons are a lot like light. Light can be thought of as, well, originally it was thought of as being waves of energy. Waves of energy. But recently we have learned that light is also made up of particles. Particles. In the same way, we can think of electrons as being particles that act a lot like waves. Waves. And that these particles, like light, will have frequency and wavelength. Frequency and wavelength. Frequency and wavelength. Okay, so those who have ears understand what I was giving them, right? Phoebe does. Good. Good. One of the things that we arrived at is an understanding that when electrons gain energy, they jump up to higher levels. But they don't have to come down like we do, or at least most of us, one step at a time. They can skip steps, take big giant steps, or take little steps. The bigger the step they take, the more energy they shed. The smaller the step they take, the less energy they shed. So when they take a great big step, we find that the light they shed corresponds to the higher frequency part of the EM spectrum. If we're talking about the visible light, what colors are we talking about? What?
The rainbow.
No. What color would you say a big giant step like this would give off? Violet, purple, blues. Okay, that side of Roy G. Biv. What if it's a teeny tiny little step? Red. What if it's a medium step? Yellow, orange, green. Okay, so the bigger the step down, the more energy they give off. Or the more, as far as the higher frequency of energy they give off. The last thing, and this is for those of you who were not here yesterday, this is what we talked about. It's really weird, but it kind of makes sense. If we were to take these 4 people, we'll have to include Marieli here. Okay, Natalie, Mark, Beth, and Marieli. And they've been dreaming of this. Could it be really? Could he do this? Give them 100 $1 bills every Friday for 30 Fridays. And tell them you have from 6 to 9 to spend it in Turkey Creek. So at 6 we drop them off. At 9 we pick them up. And we have them followed by one of you guys, carefully recording everywhere they spend money and how much. Are they allowed to use any pennies, any change? No. The dollar is the smallest increment, just like the step is the smallest increment. Okay? You can't slide, you can't make your money slide away. You have to spend your money in certain areas. Okay, so what would we find after 30 weeks of collecting data? Do you think that we'll find some patterns to the way Natalie spends her money? Folks, the answer is yes. Do you know my evidence for that? There is a whole industry now in our American commerce that makes use of that. Okay, they don't have somebody following you along, checking to see what you buy. What do they give you? Rewards cards. They'll give you a few pennies here and there, but the information they learn from how you buy, what you buy, is very valuable to them. Okay? Guess what they learn about me? I don't buy any alcohol. Okay? So if they were to make a store just for me, they wouldn't buy any alcohol in order to sell to me. I am a teetotaler. I don't buy alcohol. Okay? Could they learn some more about me? Yeah, I like hamburgers. Okay, they would have many different types of hamburgers. I'm passionate about hamburgers and tortilla chips and salsa and tomato sauce. Okay? Do you think that after studying me now for 5 or 6 years, if they were to create a store, they would know everything that I would look at, I would want to buy? Yeah. All right, gang. I say that to say that what we have discovered is the buying habits of all the elements and compounds known to man. Every element will give off light in its own particular way. In other words, every element buys, gives up money in its own particular way. Not to say that it's always following the pattern. Natalie's not always going to go to GameStop and buy herself a Game Boy game. Every once in a while she might do that. But she always goes to Five Guys, she always goes to Menchie's, and she always goes to Old Navy and buys herself a new shirt. You're not the type to go to Old Navy. You'd rather go to the collectible place and buy yourself a Avengers t-shirt, right? Yeah. All right. You would fit in really well with my family. We're just going to have to adopt you. Okay. No. So, what does this mean? This is the spending habit of hydrogen's one electron. What does it mean? It likes to, sometimes, out of 100 times, about 25 times, it'll spend a little bit of money. How do I know it's a little bit of money? Right. Yeah. Sometimes, 25% of the time, it'll spend a lot of money. 25% of the time, it'll spend a good chunk of money, not a lot. And 25% of the time, it'll spend a little bit of money. These are the 4 most likely scenarios for it spending money. Okay. Are there others? Yes. There are going to be other spectral lines, but they are not predominant, so we don't take them into consideration. This is the light fingerprint for hydrogen. And because of this, it has opened what study? What do we call it? Spectroscopy. And we will play around with spectroscopy next Wednesday. Okay? All right. So let's continue. Now that we've learned a lot, that the nucleus is down here, and there are layers around the atom that correspond to these stair steps. Now we can find where those electrons are located, right? Wrong. The original Pati Pupa, his name was Werner Heisenberg. If you like Big Bang Theory, you've heard Heisenberg's name being mentioned. If you've ever seen Back to the Future, you've heard Heisenberg's name being mentioned. This principle has been applied to various different things, But basically it says this. If you want to find where an electron is, you'll never find them. Because the very act of you trying to see them makes them go away. Now, that seems on the surface to not make any sense. But doesn't it? Think back when you were biologizing last year. You were in lab, and they asked you to find and look at an amoeba. That was exciting times, right? An amoeba. So what did you have to give the amoeba in order to be able to see the amoeba through your lenses? What? No. Even if the amoeba was dead and in a slide, what did you have to give it? Yes? Light. Light! There must be light. So in order to see an amoeba, you must shine light on it. Well, what about atoms? Well, we can't see atoms with light, but they use electron energy. It's called a scanning tunneling electron microscope, a beam of electrons. But that's still light of a sort. So what if we had a really, really powerful microscope that could see things that are as small as electrons? What would you need to give it in order to see it? Light. And what happens when you give an electron energy? It moves. So Werner killed us. People were crying when they announced this. The whole world experienced a day of mourning because everyone was wanting to know exactly where electrons were located. We were very, very sad in 1927. Some people say that it led to the stock market crash of 1929 and to the Depression. Okay, so people were depressed for almost 12 years because we could never know the exact location of electrons. Slight exaggeration there. Well, hope was not lost because near the end of the Depression, somebody said, okay, well, we need to get over it. We can't know the exact location of electrons. But could we figure out where they probably are? And everyone said, probably, yes, we like that word, probably. And they started hugging each other. And we started a war in the late 1930s because we were so excited. The Japanese tried to invade us because we had discovered that the word probably might just work. You guys didn't realize how much of an impact chemistry has had on world affairs, did you? Well, probably was a good word. And they all started agreeing, yes, probably. So they built a mathematical model to try to explain where the electrons probably are. It was called the wave mechanical model. And it's the model that you're already familiar with. It says that each atom has a nucleus, and surrounding the nucleus, most electrons are probably close to the nucleus. But as you get further and further away, you'll find that only some electrons are out here. Probably. And we came up with the charge cloud model based on the word probably. Isn't it a beautiful word? It just sounds wonderful. Probably. Probably. Okay? Will you become rich one of these days, Molly? Probably. Isn't that better than no? Okay? According to the model, electrons probably live in cities that we will call energy levels. Cities. Actually more like towns that we will call energy levels. Instead of calling them Oak Ridge and Knoxville and Connecticut and Tupelo, and don't forget Hell, that's a town in Nevada or Arizona. I always love that. I mean, you can have so much fun living around hell. You can tell people, are you going to go to hell or not? You know, it's just, I know I've been to hell in the what's that group of islands below Cuba? No, below Cuba. What's that?
South America.
No, it's a group of islands. I can't think of it. It's in the Caribbean. Oh, well.
Galapagos.
What? No, no, not that far down. I mean, it's right below it. Yeah, I've been to hell and back. Okay, these energy levels are assigned numbers. So nothing is creative as hell. They assign them numbers. So the towns closest to the nucleus is 1. Then there's a town further away, it's 2. The town further from that is 3. Further? Any guesses? 4. Beyond that? 5. No, you're not seeing a pattern. We're adding 1 to each one. After 5? 6. Natalie? 7. Yes. Next? Well, maybe we've not found an atom that is that big. Okay? Just 7 different towns. In each town, a town is going to be separated by neighborhoods, right? We have Briarcliff and Scarborough and Woodland and Glenwood and I don't know, well, I live in Emory Heights, Rivers Run, I don't know. Okay, there are neighborhoods in these towns in the chemistry world. They're called sublevels. Sublevels. Instead of being given names, they're given letters. So the closest sublevel to the center of town is called the S. The S neighborhood. Then there is P, D, and F. S, P, D, and F. Okay? So, how many neighborhoods does a town have? Does it always have all 4? Let's study that. Okay? So, the first town has only 1 neighborhood, S. Second town will have, guess how many neighborhoods? How many sublevels? 2. Very good. S and P. By the way, S actually stands for something. I'll give it to you so you can help you to remember. It stands for sharp. Hope that helps. P stands for, wait for it, principle. Principle. The third energy level has how many?
3.
That's right. You guys are seeing a pattern. S, P, D, and D. What about the fourth energy level? S, P, D, and F. The fifth energy level will have how many neighborhoods? 5. S, P, D, F, and? S. Okay, you can't start all over again. No. No.
S1.
Come on, there's a pattern. S, P, D, F. What comes after F? G. That's right. Jeez.
Why does it?
It's not
G.
alphabetic.
But S.
F. What comes after F? Come on, folks. This isn't hard. What comes after F? Every kindergarten knows what comes after F is G. What comes after G?
H.
What's the problem here? Why are you guys arguing with me?
S, P, D, and F don't come before. Wait, what?
Well,
S, P, and D don't come before F.
I don't know. This is their model. I didn't come up with this. I would have started with A.
I don't understand.
All right. So, we have a nucleus. The first neighborhood is going to be the 1S, right? The first town, S. The second town is going to have an S and a P zones, right? The third town has an S. What else? P. And what comes after P? No! The fourth town's S.
Wait, what?
And what comes after the fourth town's S? The third town's D.
No.
Good! That means you understand it. If it doesn't make any sense, that means that you are a rational human being and that you're doing just fine. Good. Why did we overlap? Why did the 4S come before the 3D? You will find out eventually. In reality, there is possibly a G, H, and I because that comes after F. We've already established that, even though you guys got all huffy with me because of it. So maybe, just maybe, eventually we will discover elements that are big enough to have electrons that live in those subdivisions. Okay? It was soon discovered that there were houses inside of these neighborhoods. In chemistry, we call these houses orbitals. Orbitals. Every neighborhood will have its own specific number of houses. Let's see if you can't see the pattern now. S has one house, one orbital. P has 3 houses.
What?
2 more. Any guesses how many houses the D will have? 5. Let's see. 2. All right, Natalie, you ready? F has how many houses?
7.
7! Because 7 is 2 away from 5. In theory, if G exists, you will have how many houses?
8, no, 9.
9, because 9 is 2 away from 7. So every higher type of property of a subdivision will have 2 more houses added to it. Okay? So, how many electrons can live in each house? Any guesses?
1.
2. So what does that mean? S has only 1 house, so how many total number of students can live? How many people can live? 2. P has 3 houses. That's 4 apart. D has 5 houses. Hey, that's still 4 apart. Hey, that's still 4 apart. 18. Hey, that's still 4 apart. There's definitely a pattern. So, if this is the nucleus, how many electrons can live closest to it?
2.
Yeah. Is that it for the first town? The first energy level? Second energy level is going to have how many different neighborhoods? 2. S and P. S. And then how many P houses?
4.
So, yes?
If only 2 can go down on the bottom one, how does the top ones that make the violet come down to the bottom?
Okay, that's a good question. Remember that more than likely it's only going to be the top ones that go into excited state because the energy can't penetrate all the way down here to the bottom. So it's these guys up here that get excited and they go up into the G's and H's and I's and stuff like that. We're describing where they're probably located in their ground state, not in their excited state. Okay, so any guesses how many total number of people can live in the third? Let's see. It's going to have an S. It's going to have a P. And it's going to have a 5D. So it's how many? 18. And the fourth floor will have an S with how many?
2.
3 P's with how many?
6.
5 D's with how many? and 7 F's with how many? So that's a total of 32. How about the 5th floor? It's going to have a, start in the beginning, S with 2, P with 6, D with, F with, G with, total of 50. Okay, this model actually was able to predict what they would look like, if we could see them, which we can't. According to this model, the S electrons are spinning around, creating a cloud that makes you think that it looks like a sphere. A sphere. Alec, almost done with that worksheet? He's smart. You too? Excellent. Okay, so where would, if this is 1s, where would you expect 2s to be? Closer to the nucleus or further away? Further away, and what shape? Okay, so it would be like this. You would not be able to see the 1s because it's in the layer inside of the 2s. What about the p's? The p's are thought to be dumbbell shaped. So the electrons are kind of moving in a figure 8 like this. Kind of. Not really, but if it helps you, there you go. Do you see why it would be called a dumbbell? If your hands are right there, you'd be kind of lifting it up. You know, the dumbbells for weightlifting. Okay, there are 3 of them. So where are they? There's one in the y-axis, one in the x-axis, and one in the z. So all together, so the 1s would be down here, the 2s would be here. Where would 3s be? You would not see this whole mess because 3s would be covering it up. Well, unless you have 3 p's, in which case you get that flower shape again. So, we have 2 electrons living in the same town, same neighborhood, same house. Will they be sharing the same bed? No, because electrons are negative. Wolfgang Pauli was able to explain this. He said this: 2 electrons can live in the same energy level, the same sublevel, the same orbital, but they will not be existing in the same place at the same time because while one is spinning clockwise, the other one will be spinning counterclockwise. Is this important? Yeah. Will you know that it's important right away? No. Will you know later? Yes. The really cool thing about chemistry is that so often it's like, what? And then it comes back around and you go, that's why. I have to teach it to you in layers. Because if I was to teach it to you as a whole, it would blow your minds. You would have gray matter oozing out of your ears. You wouldn't make it past this class. All right. So, while one is spinning counterclockwise, the other one is spinning counterclockwise. Somebody in physics last period said, well, wouldn't that make it more likely to collide? And my response was, yes. And he said, well, that doesn't make any sense. And my response was, I agree. And his response, well, what of it? Quantum theory, it doesn't have to make sense. It just has to work. Let's let Hank Green encapsulate?
Hello, I'm Hank Green. Welcome to Crash Course Chemistry. Last time we left off with Mendeleev believing he had discovered a cosmic, mystic reality about the world, when in fact he had discovered the effects of his worst enemy, tiny, invisible particles. Electrons, which are so marvelous and peculiar that it wasn't until 80 years after Mendeleev's first periodic table that they were really understood by anyone, and to this day, still very, very few people understand them. Before quantum mechanics, scientists envisioned the atomic world as just a miniature macroscopic world. Electrons seemed to just be particles orbiting around a nucleus. In fact, there was a great Dane, other kind of Dane, Niels Bohr, yes. Like certain other people I might name, he sometimes felt like he was in the shadow of his older, more successful brother, an Olympic soccer player, while Niels's handwriting was so poor that he had to dictate his PhD thesis to his mom. Nevertheless, he was an ingenious physicist. Now, you might remember a couple episodes back when John Dalton determined that elements only exist in discrete packets of matter. Well, by Bohr's time, the same thing was known for the energy given off by electrons. That energy only came off in what ended up being called quanta, which is the root of the term quantum mechanics. In 1913, Niels Bohr came up with a simple model for describing these energy levels for a single electron in hydrogen, merely assuming circular orbits. So there is some truth to the framework of thinking of electrons as particles. However, when he or anyone else tried to apply this to more complicated atoms, they failed miserably. Long story short, electrons don't really behave like particles. They're better described as waves. So we've known for like 50 years that this is an entirely inaccurate way of visualizing an atom. Nuclei, yeah, you can think of them as solid particles, but not electrons. Electrons are wave-particle dualities. Now it is time to move a little bit into the realm of metaphor here, because I'm going to tell you how I think of electron shells and orbitals. Not really how they are. The music of electrons is not simple music. It's no three-chord song. It's like Beethoven, but with more rules. Hard, fast rules that can't be broken. In that way, at least, it's more science than art. Electrons exist in orbitals, a bit like the individual notes on a keyboard. But the orbital's tone isn't complete until it has two electrons in it. And orbitals exist in shells. The first shell just has a single orbital, an s orbital, which can only fit two electrons. That's why the first row of our periodic table only has two elements. They play a simple song, those two, and a song that every other element will build upon. The second electron shell, though, is physically larger and thus can include more than just the s orbital. A second sort of orbital with three different configurations is added, the p orbital. Instead of just being a single tone, the p orbital is more like a three-part harmony, with two electrons in each part for a total of 6. Those 6 electrons of the p orbital plus the 2 s electrons are the 8 electrons referred to in the octet rule, the desire for most of the lighter elements to have 8 electrons in their outer shell, just like a musical scale. This is often described in terms of fullness or satiation, as if the atoms are like devouring electrons, but I prefer to think of an incomplete electron configuration as a cacophonous symphony playing at different keys and different tempos. The closer you are to harmony, the worse it is, until one final note chimes in, that 8th note, and everything crisps into full resolution. A deep, complex tone emerges and the atom settles into complete harmony. The harmony of the noble gases. That's just how I think of it. And just like with music, there's a bit of notation to learn as well. It's important to know how to write out what we call electron configurations, a condensed way of showing exactly where all of an atom's electrons are. First, we write the number of the shell, then the letter of the orbital, then the number of electrons in that orbital, and repeat until we run out of electrons. So for hydrogen, with just one electron, it's 1s1. For fluorine, it's 1s2, 2s2, 2p5. So if we're trying to understand reality, we should not think of electrons as circling around the nucleus of an atom like planets around a star, but instead as an excitation around the nucleus. And the shape of that excitation is the orbital. Orbitals are precisely the reason that everything exists. They are the root and the key and the nexus and the crux and the keystone in every other metaphor of not just chemistry, but existence.
All right.
Hello.
Oh.
I'm Hank Green.
Okay, so tomorrow we're going to play a game that will have nothing to do with any of this. It'll be a game that we will play for fun and will have nothing to do with this. And you should believe me, because I never lie to you.